Okay, this is lesson 8.2. It's really section or chapter 5, but it's the 8th unit, so 8.2, talking about the graphs of the sine and the cosine function. Some of this is going to be review from what you learned in Algebra 2. We did talk briefly about graphing sine and cosine, and we just did very basic graphs. So we're going to take that and expand upon it. You're going to go into much more detail, much more depth. So this part right here, this first objective, is what you might remember from Algebra 2, the parent functions, talking about what the amplitude and the period of the sine and cosine. Many of you may not have gotten far enough in Algebra 2 to talk about vertical transformations or some of the horizontal transformations. So, kind of a long lesson. There are quite a few examples. So buckle up. I'm going to try to go slow so you can take some pretty good notes. You're going to need these. This lesson right here is going to be pretty much the main lesson of this next unit. Most of the test questions are going to come from this lesson right here, from lesson 8.2 or section 5.2 in your textbook. So this is one you're going to want to pay really good attention to. So first off, the sine and the cosine are what are called periodic functions. They're called periodic functions because their graphs have a repeating pattern, which you'll see here in a second. I'm sure some of you are already visualizing in your head what the graph of sine and cosine are because you've seen them before. They're much like a sound wave. They go up and down and up and down and up and down and up and down over and over again. Their domain is all real numbers, so there's no end to the graph, to the right or to the left. Those types of functions are called periodic. Sine and cosine are the only examples of periodic functions. There are many more, but these are the ones we're going to study in 8.2. So in case you've forgotten, let's take a quick look at each of the parent functions, the sine first and then the cosine. Parent function means just a function with no transformations. It hasn't moved up or down, just a basic function like y equals x squared or y equals the square root of x. Just parent functions with no transformations. Now, I'm sure you have a basic idea or some of you have a basic idea of what the graph looks like, but let's be a little more exact than just going up and down and up and down. Make a table of values. Now you might recall the input for trig functions are angle measures. So this column is going to represent angle measures in radians. Everything's going to be graphed in radians. Okay. The output, if you remember from our discussion last time from section 5.1, I get a unicircle up here. Since we're talking about the sine function in particular, the input, we're just going to have these radian measures. Okay. The output is going to be the y values, y values. The sine, according to what we talked about last time, the definition of the sine function when we're talking about radian measures around the unicircle are the y values of the points at those angle measures. So just to keep it brief and basic, the first radian measure we're going to choose would be a radian measure of 0. So we're taking the sine of 0. So again, referring to the unicircle, here's 0 radians. The y value at 0 radians equal to 0. So if x is 0, then y is 0. That's the first point on the graph. The next value we're going to choose, we're going to keep these all quadrantal angles, so angles that lie on either the x or the y axis. We're going to choose pi halves. That's at the top of the unicircle here. This is pi halves or 90 degrees. The y value at 90 degrees or pi halves is equal to 1, so pi halves comma 1. The next quadrantal angle would be pi. So again, referring to the unit circle, if we go over here to pi, the y value there is 0. The next quadrantal angle would be 3 pi halves. That's down here at the bottom of the unit circle, 270 degrees or 3 pi halves radians. The y value there is -1. And if we complete the full circle and end up at 2 pi, we'd be back to 0. Now here's the periodic or the repeating pattern part. If we kept going indefinitely on the x-axis, so let me get this up here. Let's see if I can. There we go. So we've gone all the way around the circle. If we go up in the same number of increments, so we go to 90 degrees, we've gone all the way out around the circle, plus another 90 degrees, or plus another pi halves. That's equal to 5 pi halves. So if we did continue this table, the next one would be 5 pi halves, but that's nothing more than pi halves. And that would have the same y value of 1. So we'd get this part of it again. If we went all the way around a circle and then added another pi, that would be 3 pi. So the next value would be 3 pi, but again, that's just the same as pi, so it would be 0. Then if we went all the way around a circle plus another 3 pi halves, that's 7 pi halves, which would be a y value of -1. If we all the way around a circle twice, that would be 4 pi, which would be another y value of 0. So the pattern in the y column, 0, 1, 0, -1, would just repeat 0, 1, 0, -1. So taking a look at now at the graph, now it's not super important, and I tend not to be real picky on this, but the scale of the x and the y axis really ought to be the same. We're talking about 0 and then pi halves and then pi. Pi right here is 3.14. It wouldn't make much sense to put pi right here, because that's about the same distance from here to here on the x-axis as it is from here to here on the y-axis. So you gotta sometimes be mindful of the scale on your axes. So I'm gonna call this one pi halves. Call this one pi. 3 pi halves and 2 pi. So 0, 0, pi halves, 1, pi, 0, 3 pi halves, -1, and then pi halves. Now even though I don't have it on my table, if the pattern continued, we would have 5 pi halves, then 3 pi, then 7 pi halves, then 4 pi. So go up to 1, back down through 0, down to -1, and back up through 0. So connecting these, we go on forever to the right, and this graph actually does extend to the left as well. Now, there's two words you might remember from Algebra 2 last year. There's amplitude and there's period. The amplitude is half of the distance between the highest and the lowest point. So on this graph here, 1 is the highest point, -1 down here is the lowest point. If we measured that distance between the highest and the lowest, between -1 and 1, that's a distance of 2, but the amplitude is half of that distance. So in this case, the amplitude is equal to 1. The period is the horizontal length or distance needed to complete one cycle. That's the period. It's the horizontal length needed to complete one cycle of the graph. Sine and cosine have an infinite number of cycles. You just have to know where one starts and where one ends. So in the parent function, we're going to start a cycle right here at the origin, 0, 0, then it goes up to 1, back down through 0, down to -1, and then it's back where it started again. That's one cycle. So from here all the way to here, here's one cycle. From here all the way to there, there's another cycle. And notice they both have the exact same horizontal length. One of those lengths is called the period. So if we take a look, if we started at 0 on the x-axis and that cycle is done right here, then that's a period of 2 pi. So the thing to remember here about the sine function, the parent function of the sine, the amplitude is 1, the period is 2 pi. Also important to note is where the function starts. It starts at the origin 0, 0, because when x is 0, the sine of 0 is also 0. Now cosine, we're going to do the same thing. Start with x equals 0, but if you notice on the unit circle, here the unit circle with 0 radians, the x value now is what we're looking at because we're doing cosine, and on the unit circle, cosine is equal to the x value of all the points. So if x is 0, then y is 1. So the first point on the graph is actually point 0, 1. Now using the same increments for x, we're going to have pi halves, and then pi, 3 pi halves, and then 2 pi. So if we go to pi halves, right up here, the x value is 0. If we go over here to pi, the x value is -1. If we go to 3 pi halves, the y value is 0. And if we go all the way around the unit circle to 2 pi radians, the x value is 1. So it's still a similar pattern, just starts in a different spot. Instead of going 0, 1, 0, -1, 0, it goes 1, 0, -1, 0, 1. So for pi halves, then pi, then 3 pi halves, then 2 pi, then 5 pi. Now we're going around the circle one more time. 5 pi halves, 3 pi, 7 pi halves, and 4 pi. So we have 0, 1, pi halves, 0, pi, -1, 3 pi halves, 0, and then 2 pi. Notice we're where we started, back up at 1. So this would be one of the cycles right here. And notice the horizontal length that took to complete a cycle. It was the same as 2 pi. And we go here, if the cycle continues, we go down through 0, -1, 0, and then back up. So there's another cycle. So here's the amplitude. If we measured the amplitude, the highest point right here is 1, the lowest point down here is -1. Again, that's a distance of 2, but the amplitude is half of that. So the amplitude is 1. Period. We measured from the start of the cycle. We started at its highest point here and stopped where the graph is again at its highest point. That's a horizontal distance of 2 pi. So the period is 2 pi. Now, these are just the parent functions. What we have to start looking at is what happens when we start putting numbers in front of the function or outside of the function here. So, taking a look at this right here, this is a dynamic software where you can make changes, and according to the changes that you make, the graph changes accordingly. So, focusing on A, if you take a look at where A is, A would be in front of the function, and the function I have now is just a sine function. It starts at 0, 0, the amplitude is 1. Okay. You notice along the x-axis now I have radian measures. Along the y-axis I have just normal integers. So if I start messing with a, the number in front of the function, notice right now it's 1. So if I start increasing that value of a right here on the slider, if a increases, notice what's changing on the graph. The amplitude is changing, and it's changing exactly according to the change in a. If a becomes 3, then notice the highest point here is 3, the lowest point is -3. That's a total distance of 6, so the amplitude would be 3. So identifying the amplitude from the equation of the function is really easy. The number in front, that's multiplying in front of the sine or the cosine, is exactly equal to the amplitude. If the number gets larger and larger, the amplitude increases. If the number gets smaller and smaller, the amplitude decreases. It also can get smaller than 1. If we end up with decimals or fractions, the graph becomes more flat. Notice what happens when a becomes negative. So now it's at -1. The one that's in blue is the original function here. The one here that's in black is the transformed function. The only difference really is from the initial point, instead of starting at 0, I'm going up to the highest point. If there's a negative number in front of the sine function, it starts at 0, 0 and goes down to its lowest point. Basically, it's a vertical reflection over the x-axis. So that's what happens with A. A affects the amplitude. Let me change it back to 1. Now we're going to talk about B and C here in a couple of minutes, but the other one I want to talk about is K, the effect that K has. Notice, first of all, where K is. It's outside of the function. These transformations here occur inside the function. So any kind of transformation that occurs outside of the function, like A was a vertical change. And since K is outside the function, it's also going to be a vertical change. But notice the effect that K has. As I start increasing K, all it does is move the entire graph up if K increases. If K is decreasing and becomes negative, it moves the entire graph down. But notice it retains the shape. The amplitude stays the same. This is called a static transformation. Retains the shape of the graph, just moves the location. So these are the type of transformations we're talking about now. We have values of K which move the graph up or down, or we're going to have values of A that are going to change the amplitude of the graph. So coming back here, we're going to look at different functions that have different values of A and possibly different values of K. So first of all, just to keep things simple, we're going to change the amplitude. Okay. What isn't going to change is the period. All of these 4 examples are going to have the same period of 2 pi, because we haven't talked about what changes the length of the period yet. So for this one, y equals 2 times the sine of x. Notice it's a sine function, so that lets us know we're going to be starting at 0, 0, the origin. But the amplitude, the number in front here is 2. So what that means is on the y-axis, we're going to go as high as +2 and as low as -2. The x-axis, 1 cycle, and that's all I'm ever going to require you to graph on your homework and on your test is 1 cycle of these. So since the period has remained unchanged, one cycle is going to take a horizontal length of 2 pi to complete. So starting at 0, 0, and since it's the +2 and not a -2, it's going up first to its highest point, then down through 0, lowest point, and then the cycle ends exactly where it began, right here at 0. And that's one complete cycle. Now notice this is exactly what I'm going to require of you guys on an exam. One cycle needs to be broken up into 4 subintervals. Okay, definitely where the cycle ends and halfway between the cycle, and then these other 2 tick marks. Not only do you have to have the tick marks, but they have to be labeled in radians: pi halves, pi, 3 pi halves, and 2 pi. You need to have those 4 intervals or subintervals clearly labeled. Okay, and then the amplitude as well, 1 and 2. For part B, cosine, the difference here is where the graph starts. It's not going to start at 0, 0. In the example of cosine, it starts at the highest point. of its amplitude. So now we look to 4, the amplitude. So on the y-axis, we'll be going as high as 4. And as low as -4. X-axis, again, since the period hasn't changed, we're going to go all the way out to 2 pi to complete one cycle. So since this is a cosine, it's going to start at the top of its amplitude, and at the end of the cycle, it's also going to be at the top of its amplitude. And since this is as high as the graph can go, this is the top of the amplitude, it has to go lower, so it's going down through 0. Now it's down at its lowest point, back up through 0, and the cycle ends right there. So this one cycle of that for cosine of x looks pretty much like that. Now, part C and part D have not only an amplitude change right here, but also a static vertical change. It's going to move the graph, in this case, down 2 units. So keeping that in mind, here's what I would suggest. Let me change this axis a little bit. So what I would do, especially when there's static transformations like this one that moves the graph down 2 units, or in a minute when we talk about static horizontal transformations that move the graph left or right, I would do what's called transforming the origin. We've seen something like this before. You might remember when we were graphing conic sections. Rather than thinking about moving the hyperbola or the ellipse, we actually transform the origin according to the transformations here. So we have a transformation that's down 2 units. So I'm going to take this origin, transform it down 2 units, and I'm going to superimpose onto this graph a new coordinate system. And consider this now to be 0, 0. Now there haven't been any static transformations moving the graph left or right. So we're going to keep the origin on the y-axis and just move down 2 units. This is going to be pi halves, pi, 3 pi halves, and 2 pi. Now, the amplitude is 3, but that doesn't mean it's going to go up to 3 and down to -3 because we've had a vertical shift down 2 units. So if we consider this to be the new 0, 0, then from here we're going to go up 3 units, 1, 2, 3. So we're actually going up to +1 on the original y-axis, and then down 3 units from the new origin, which is actually -5 in relation to the original origin here. And since this is a cosine graph, it's going to start at the highest point, and at the end of the cycle, it'll be at its highest point. It goes down through 0, its lowest point, back up through 0, and at its highest point. Now for part D, we have a couple of things happening here. We have a change in the amplitude. So the amplitude is increasing. We also have this minus sign, which flips the graph upside down. So instead of starting at 0, 0 and going up to its highest point, it's going to start at 0, 0 and go down. And then we have this vertical transformation up 1 unit. So what I'm going to do is actually take the origin 0, 0, shift it up 1 unit to 0, 1, and superimpose onto the original graph a new coordinate system. Consider this now to be the origin, the shifted point that's been moved up 1 unit. Since there's been no change in that period yet, we can use the same marks we've been using, pi halves, pi, 3 pi halves, and 2 pi. Now, the amplitude is 2, but again, it's not going to go up to 2 and down to negative 2, because we're moving up 1 unit. We're still going to go up 2 units from the new origin, so we're going to go up 2 units, but that's really 3 on the y-axis. And we're going to go down 2 units from the new origin, but that's really negative 1 on the original y-axis. This is a sine function, so it starts at 0, 0. Normally we go up to its highest point. Because of the vertical reflection, this minus sign is going to start at 0, 0 and go down to its lowest point, back up through 0 up to its highest point, and the cycle ends where it started, right there on the axis. So this graph is going to look like that. It's just been flipped upside down. Now, the horizontal transformations seem to be a little bit more challenging to most students. There's change in the period affecting the horizontal length needed to complete a cycle. That's a horizontal stretch or compression. There's also something called a phase shift. That's a static horizontal shift. What that means is the graph just moves to the left or to the right, but it doesn't affect the period. So those are the two things we're going to look at. First, we're going to look at a change in the period, and then we're going to look at a phase shift, or a shift that moves the graph to the left or to the right. So going back to this dynamic software here, we've already looked at the effects that A and K have. Those were the two vertical transformations. A affected the amplitude. K was just a vertical shift up or down. So now I have to focus, if you look where my mouse is, we have to focus on B and C. Let's focus on B first of all. B would be the number closest to X. So, and this is gonna be the transformation that affects the period, this value of B. Now, you might think if B increases, then the period is going to increase, but you need to remember that I've used this phrase over and over again. If it's inside the function and B is considered inside the function, then it has the opposite effect. So if B actually increases, the opposite of that would be to decrease the period. So if you take a look at what happens, B is getting larger and larger and larger, but what's happening here to the period? What's happening to the graph? As B continues to get larger and larger, you see that the graph, the one here in black, the length needed to complete one cycle has gotten shorter, so the period is decreasing. So as B increases, the period decreases, and vice versa. As I decrease B, and as B gets smaller and smaller and closer to 0, so now B is taking on fraction values or decimal values, the length needed to complete a cycle, if you can tell here on the function on black, the length needed to complete one cycle increases. So it's having the opposite effect. Now, you might have guessed C then is going to represent the phase shift or the static transformation. So as C changes, you can see that the graph is moving right or left, but the shape is remaining the same. It's not changing the shape. That's why it's called a static transformation. It just moves the graph to the left or to the right. Now notice on the equation part of this, if it's x minus 1.8, take a look at what's actually happened to the graph. It's shifted to the right. And again, that's just that old phrase of inside the function is opposite. So if it's minus C, that moves it to the right. If on the equation you notice it becomes positive values, take a look at where the graph is moving. It's moving to the left. So those are two types of transformations we need to take a look at right now, is the horizontal transformations. So first, a change in the period. So given y equals the sine of b times x, or y equals the cosine of b times x, you can find the period algebraically by using this formula, 2 pi divided by the absolute value of b. This is something that you will absolutely need to remember, this formula. It won't be given to you on the test, you're just going to have to know it. So you take the value of b, 2 pi divided by b, or the absolute value of b rather, is equal to the period. Just in case you've forgotten, on a parent function where there is no value in front of the x, really there is a value, there's a 1 right there. So if there's a 1 in front of x, then the period is just 2 pi. But once you start putting numbers in front of x, that affects the period, either increases it or decreases it. So a couple of examples here. Example 2, we need to find the amplitude and the period, and then sketch the graph. So we're keeping it real simple here to begin with. We're not having any type of static transformation, so the graphs are not moving up or down or left or right. There's an amplitude change here with the 2 that's in front of the sine function, and there's a period change here. So notice the directions are very specific, and this is for a reason. Before graphing a sine or a cosine, you should always find the amplitude and the period. So for part A, the amplitude is going to be 2. Now for the period, you have to remember to use this formula, 2 pi divided by the absolute value of b, where b is the coefficient of x. So it's 2 pi divided by 2, which is pi. So what you have to think of here is, has the period increased or decreased? Normally it takes a horizontal length of 2 pi for these graphs to complete one cycle, but in this function here, the period is going to complete a cycle, or the graph's going to complete one cycle in just a length of 1 pi. So the period is actually decreased. So on the y-axis, we're going to go as high as 2 and as low as -2. But the cycle starts at 0 and is going to end at pi. So this needs to be broken down into 4 equal subintervals. So half of that is pi halves, but then half of that is pi fourths. And then this one here is 3 pi fourths. Those need to be labeled. Okay, not labeling these subintervals is going to cost you a couple of points on an exam. So this is the horizontal length needed to complete one cycle from 0 to pi. Since this is a sine function, the cycle is going to start in the middle. 0, 0 in this case is going to go up to its highest point, back down through 0 to its lowest point, and then back up through 0. For part B, a couple of things to notice. There isn't a number, or there doesn't appear to be a number in front of the function. There really is. There's a 1 right there, so that means the amplitude is 1. And it's a problem like this that quite often gives students a little bit of trouble early on. The period, the formula is 2 pi divided by the absolute value of b, where b is the coefficient of x. Sometimes it's hard for students to identify the coefficient in this kind of a situation. Cosine of x over 4. The number directly in front of x is 1, but what's happening to the 1? 1 is being divided by 4, so the coefficient is truly 1/4. Another way to think about this function is y equals 1/4. Sorry, y equals cosine of 1/4 x. The one over here in red that we started with and one here in blue, these are exactly the same. So the coefficient of x is 1/4, that's b. So we're dividing by 1/4. 2 pi divided by 1/4. Dividing by 1/4 is exactly the same as timesing by 4. So it's 8 pi. I need to decrease that because the period is increased by quite a bit. So the amplitude is still the same. It goes as high as 1 and as low as -1, but the cycle is going to end all the way out here at 8 pi. So now you need to break that cycle up into 4 equal subintervals. 4 pi, 2 pi, and 6 pi. And because we're graphing a cosine, that's going to start at the top of this amplitude, go down to 0, that was lowest point, back up to 0, and then ending at the top
of its amplitude. So there's one complete cycle of y equals cosine of x over 4. Now for part C, amplitude. Now amplitudes can never be negative. There is a negative sign in front of it, but the amplitude is always positive because it's a distance. So it doesn't make sense to have a negative distance. The amplitude is 3. The effect that minus sign has on the graph is just reflects it vertically. So it's going to start at 0, 0 and go down instead of going up. Period is 2 pi divided by b. Again, where b is the coefficient of x. In this case, it's pi. 2 pi divided by pi is just 2. So we have 1, we have 2. So this is actually the horizontal length needed to complete a cycle. So it needs to be broken up into 4 equal subintervals. So this is 1/2. Then we have 1, and then we have 3 halves, and then we have 2. Now, since the sine function starts at 0, 0, and because it's been reflected vertically, instead of going from 0, 0 up to its highest point, it goes from 0, 0 down to its lowest point, back up through 0, 0, up to its highest point, and the cycle ends where it starts at 0. That's what that graph would look like. Alright, part D is a little more challenging. There's a lot happening here. We have a amplitude change, we have a period change, and the graph is also moving up one entire unit. So I'm going to focus on this one first. Because there's a static transformation happening here, I would recommend that you shift the whole entire origin. So I'm going to move up 1 unit and draw a new axis system where the origin is that shifted point, 0, 1. Now identify the amplitude. In this case is 1/2, so it's going to be a very flat graph. Period is 2 pi divided by the coefficient. Here the coefficient is clearly 1/2, so it's 2 pi divided by 1/2, which is 4 pi. So go 4 pi way out there, middle. We have to break this up into equal subintervals, so halfway is going to be 2 pi, and then 1 pi, and then over here is going to be 3 pi. Now this is cosine, so the cosine starts at the top of the amplitude. If we're starting at this new origin point right here, then the highest it's ever going to go is that 1/2 mark. The lowest it's ever going to go is this 1/2 mark below the new origin. Now to label these, this would actually be 3 halves, and that would be 1/2 on the y-axis. So the graph's going to start at the top of its amplitude. It can be a very flat graph. Goes down through 0 to the lowest point of the amplitude, which is right there. Back up through 0, and at the highest point. So those are all examples of primarily changes of the period. Let's now get into what are called phase shifts. Now, you're going to see this 2 different ways. So I have 2 different things here you have to be very careful that you copy down exactly. The biggest difference, if you haven't noticed it, or if you didn't notice it, the biggest difference, and this is something that you absolutely have to pay attention to, is where is B? Is B directly in front of X, part of inside the parenthesis, or has B been factored out? It's still in front of X, but it's factored out in front of the parenthesis. That makes a huge difference in the phase shift. The phase shift is the amount that the graph is moving left or right.
So
if b has not been factored out and it's inside the parenthesis, then the graph is going to move right or left according to this formula, the opposite of c divided by b. That's the phase shift, negative c over b. If you're lucky, b has already been factored out in front of the parenthesis, not factored out in front of the function, because that would be a vertical change if it's outside the function. It's still considered inside the function because you're still taking the sine of b and also x minus c. So it's inside the function, but it's outside the parenthesis. In that case, the phase shift is just the opposite of c. That might not be totally clear right now, but you'll see a couple of examples where b is inside the parenthesis or where it's outside the parenthesis. Now remember, these phase shifts, these are static horizontal transformations, so the graph keeps the same shape, it just moves to the right or to the left. The only thing with a change, depending on b is what's changing the period, it's not the phase shift. So, again, we'll start off real simple. For example C, we're going to graph y equals cosine of parenthesis x plus pi halves. Now notice there is no amplitude change. There's nothing in front of the function to change the amplitude. There's also nothing directly in front of x, neither here inside the parentheses nor outside of the parentheses. So there's nothing affecting the period. The amplitude is 1, the period is 2 pi. What we have, however, is this phase shift, this static transformation right here to the left. And why is it to the left? Well, it's x plus pi halves, and you got to remember anything inside the function is opposite. Something you might be a little more, I'm going to move this to the side. If the function were y equals x plus 2 to the second power, this plus 2 would move the graph to the left 2 units. Or if the function were y equals the square root of x plus 2, that moves the graph to the left 2 units. So this right here, this x plus pi halves, is going to move the entire graph by a factor of pi halves. Now, because this is a static transformation, I would recommend that you shift the origin. So we have normally the origin here is 0, 0. But, I'll label this here. Get some. So if this is pi halves and pi and 3 pi halves and 2 pi, then this would be negative pi halves. It should be more like right there. So because the graph is shifting to the left by a factor of pi halves, I'm going to take the origin, shift it over to pi halves, and create a new axis system centered around that point, negative pi halves, 0. And then graph everything as if this were the original origin. So the amplitude is still going to go, the amplitude remains unchanged. It goes high as 1 and as low as negative 1. And the period, matter of fact, we should state those. The amplitude is 1. The period is still 2 pi divided by b, but there is no number directly in front of x, so b is just 1. So it's 2 pi. Now, normally if the graph started at 0, 0, it would end at 2 pi. That's the length of one cycle. Now the length is going to stay the same of this cycle, it just has to shift over a factor of pi halves. So it's going to start at 0, 0, and if we retain the same horizontal distance, it's going to end at 3 pi. The cycle is going to end at 3 pi halves. Now, I stated that incorrectly. We're actually doing cosine, so it's not going to start at 0, 0. The cosine graph actually starts at the top of its amplitude, and if we retain a distance of 2 pi units, that's going to end right here at 3 pi halves. So then the cosine goes down through 0. It's at its lowest point, back up through 0. Now it's at its highest point. That's the end of the cycle. So the phase shift, if you wanted to label that, is negative pi over 2. The phase shift represents where the graph moved horizontally. Since it moved to the left, the phase shift here is negative pi over 2, whereas inside the function here it's x plus pi over 2. Okay, for part B, so we have a couple of changes here. This 2 in front of the sine function is affecting the amplitude, so it's going as high as 2 and as low as negative 2. Now, this right here, x minus pi over 4, because there's nothing in front of the parenthesis, nor is there anything in front of x directly inside the parenthesis, this is the actual phase shift, and since it's x minus pi fourths, it's moving to the right by a factor of pi fourths. Now, if we call this 2 pi and pi halves, then pi fourths is actually right in between 0 and pi halves. So right here would be pi fourths. So that's where I'm going to draw So we're going to consider this now to be the origin, pi halves comma 0. Now amplitude is 2. Period is 2 pi divided by b, where b is the coefficient of x, either inside the parenthesis or outside here. It doesn't matter. That's still b either way, but it's 1. So it's equal to 2 pi. Now, if the graph had started from 0, then it would end at 2 pi. But it moved over by a factor of pi fourths. So normally ending at 2 pi, if we move that over a factor of pi fourths, that would be right here. We have to label that. So all you got to figure out is what is 2 pi plus, moving it to the right, pi fourths. So if we get a common denominator, 2 pi is going to be 8 pi fourths. So 8 pi fourths plus another pi fourths is 9 pi fourths. Now, normally, the middle point of the period, if the period is 2 pi, would be 1 pi, but everything, remember, has been shifted over by a factor of pi fourths. So that would be 5 pi fourths. And then this would be, what I'm doing here is breaking this up into equal subintervals, like we've talked about. So halfway between here would be 3 pi fourths and 7 pi fourths. So again, all of those subintervals need to be labeled. Now, since we're doing a sine function here, start at 0 comma, or what we were calling 0 comma 0, the new origin, and then at the next subinterval, it's at its highest point, it's going up. Then at the next subinterval, it's at the lowest, it's in the middle, 0 comma 0, then it's at the lowest point, and then the cycle ends here at 9 pi fourths, back at 0. So that's one cycle. So now we're getting into some of these that have not only an amplitude change, but a period change. Now just so you can see these together, part C and part D, notice what the difference is. Here in part C, the period change occurs in front of the parenthesis, whereas here the period change occurs inside the parenthesis. That makes a difference in how you describe the phase shift. It makes a big difference. So part C first. Amplitude is 3. Now we have to be careful about the period. The period is 2 pi divided by b. In this case, b is 2. The period is pi. So now the horizontal length needed to complete one cycle has decreased. So it's a horizontal compression. Now the phase shift, because b has been factored to in front of the parenthesis, this value, or the opposite of this value rather, is the phase shift. So it's moving to the left by a factor of pi units.
So again, and actually for this particular example, part C, it may not be absolutely necessary, but I just want you to get into the habit. Whenever there's a static shift, whether left, right, up, or down, I want you to get used to shifting the origin. So just using our normal subintervals, here we have pi halves, pi, 3 pi halves, and 2 pi. Here would be negative pi halves. This would be negative pi. So because the phase shift is negative pi, then the origin is going to be, it's actually a little bit off. According to scale, being a little bit more like right there. Anyway, because it's moving to the left by a factor of pi, I'm going to put a point there and consider that to be the origin. Okay. Now consider the length needed to complete one cycle. The length is 1 pi. So if I start at negative pi here and then measure a distance of pi units, then that cycle is going to end right here at 0. And then another cycle would end at pi, another cycle would end at 2 pi. So because this is where one cycle is occurring right here, this interval needs to be broken down into 4 subintervals. So here and here. So this is negative pi halves, this would be negative pi fourths, this would be negative 3 pi fourths. And then the amplitude is 3, and since we're graphing a cosine function, the cosine function starts at the top of its amplitude. It's going to come down through 0, and then down to the lowest point of its amplitude, back up through 0, and then the cycle ends at the highest point of its amplitude. So what I was mentioning a few minutes ago, it may not have been absolutely necessary to shift the origin in this particular case because the phase shift was exactly equal to the period. So we could have just graphed the cycle starting from here and would have been exactly the same. It would go down, then back up, and then the next cycle would go down and back up. I do want you to get used to, anytime there's a static transformation, just get used to shifting the origin. So for part D here, the amplitude is 2. Now the period is 2 pi divided by the coefficient of b. Whether it's inside or outside the coefficient of x, we need to determine the coefficient of x. So it's right here, this time it's inside it. There's a 1 directly in front of it, and that's being divided by 2, so b is equal to 1/2, which is 4 pi, so this cycle doesn't actually end till all the way out here at 4 pi, but now we have to consider the phase shift. I'm going to write this down here. I know it's a lot to keep track of, but this is not the phase shift. Okay, because b is inside the parenthesis directly in front of x. The phase shift is the opposite of c divided by b, where this is c. Now the opposite of c is going to be positive pi fourths. That's going to be divided by b, which is 1/2.
Now remember, dividing by 1/2 is exactly the same as multiplying by 2 over 1. So pi fourths divided or multiplied by 2 is pi halves. So the phase shift here is pi halves. What that means is we're moving to the right by a factor of pi halves. So, since it's a static transformation, I'm going to move the origin. And now, since the period is 4 pi, if we started from the original origin and went over a distance of 4 pi, then the cycle would end at 4 pi, but we have to shift over by a factor of pi halves. So if we take 4 pi and add pi halves, then 4 pi is 8 pi over 2. Adding pi halves would be 9 pi halves, so the cycle ends at 9 pi halves. Normally 2 pi would have been the middle point, but if you shift over by a factor of pi halves, this is the middle point. We're breaking this up into its subintervals here and here. This is 3 pi halves. This is 2 pi right here, so this would be 5 pi halves. This would be 3 pi, so this would be 7 pi halves. So I'm labeling the subintervals. Because this is a sine function, it starts in the middle of its amplitude, or in this case, our quote-unquote 0, 0. And then the next subinterval is at its highest point, lowest point, or sorry, the middle, and then this next interval is at its lowest point, and then the cycle ends way out there at 9 pi halves. Alright, last one here. We're going to put everything together. We have a vertical shift up, we have a horizontal shift to the left, we have a period change right here with the 2. There, fortunately for us, is no amplitude change. So, let's see what this is going to look like. So we're taking a look, the amplitude is 1. Not because of this one right here. Remember, the amplitude is the coefficient that's multiplying the trig function. This, since it's adding outside of the trig function, is just a vertical shift up 1 unit. The period is 2 pi divided by, in this case, 2. So the period is pi. Now the phase shift is the opposite of c, which is negative pi. This is c right here, divided by b, and the reason we're using this formula is because b has not been factored out to out front of this parenthesis, it's inside, so we have to take that into account for the phase shift. So the phase shift is negative pi halves. That means we're moving to the left over here to pi halves. So there's two static transformations occurring here. There's the shift up 1 unit here, and then there's this phase shift to the left pi halves. So we're going to go left pi halves and up 1. And then that's where I'm going to graph or place the new origin. I'm keeping everything the same scale. So the period, the length of the cycle or the period is pi units. So starting at the y-axis going out here, this would be a length of pi, but if everything is shifted over by pi halves, then we start here at negative pi halves and end at pi halves, positive pi halves. That's a horizontal length of pi units. So that needs to be broken down into subintervals. This would be pi fourths. This would be 0. This would be negative pi fourths. Now this is a cosine function, so it's going to start at the top of its amplitude. The amplitude is 1, but it's been shifted up 1 as well. So it's actually going to start at 2. And the cycle here is going to end at 2. It's going to go down through 0, the lowest point here, and then up through 0, and its highest point.
Now, if you like to do things on your calculator, it's fine to graph these on your calculator as long as you make sure that you know how to use your own dang calculator. One thing that you want to have to do is change the mode. We've been dealing primarily in degree mode, but we're graphing these in terms of radians. So switch it to radian mode. This one, for example, could be 1 plus cosine of 2x plus pi. Now, I don't generally recommend that you mess with what's called the window. What the window is, depending on how well you know how to use these calculators, the window describes the dimensions of your axes. Right now I have it set that the x min, or how far to the left, is going to be negative 23.5. The x max, or how far to the right, is 23.5. This is fine when you're graphing polynomial graphs or normal type of graphs. Trig graphs, this actually wouldn't be a very good viewing window. So if you hit the zoom button, notice the 7th option is zoom specific to trig functions. So I'm going to hit option 7. Now it graphs a number of cycles, but most importantly, okay, there's a point here, 0, 0, it comes up. If you hit the trace button, graph up to the top there. So when y is equal to 2, we're at 1.57, which is pi halves. So just a quick little way to make sure that your graph is accurate. And that's it. That's what you need to know for graphing sine and cosine. Notice we didn't do any tangent because it's completely different than these, and many of you probably didn't even graph tangent last year. So next lesson is going to involve graphing tangent, plus all the other ones, secant and cosecant.